All right, I believe we're on 122. Is that correct? All right, so we've been talking about where an original function is increasing, where is it decreasing, where does it have a max, where does it have a min, and we can determine all of those different characteristics or properties based off of the derivative, aka the slope. And the few examples we did yesterday were graphical ones where we were basing our analyses off of a picture of a function, whether it was the original function or the derivative. Okay, it could be either one of those graphs, and how you interpret those graphs are different depending on which one it is. We're going to take an analytical approach today, which just means by hand, okay, using some algebra to help us figure out where's a function increasing, where's a function decreasing. So no graph in this case. We're just going to do a lot of analysis using charts, algebra, math, the good stuff. Okay? So for each of the given functions, determine the intervals where f of x is increasing or decreasing. Find the coordinates, meaning the x value and the y value, of any extrema. Extrema just means a max or a min, okay, high point or low point. Unless otherwise noted, the domains, all real numbers, provide justifications as usual. Okay, so one key thing here that we're going to discuss, we're going to introduce kind of a vocabulary term to help us with this. We're going to need to find critical points. We've actually been discussing these already. We just never used the term critical points before. Critical points are x values where a function has a potential or possible max or min. Okay, so possible locations where we have a high point or a low point. Do we know what the derivative or slope is at a high point or low point? 0, okay, so aka the derivative of the function is 0. So that's a key analysis or property that we can use. We're also going to add something in here. The derivative is 0 or it doesn't exist. Or it's undefined, however you want to phrase that. We're not really going to see the does not exist aspect of these critical numbers until later this year. Okay, for right now, we've only been discussing slopes of 0. Okay, so I'm just going to add that in there so it's in your notes, but we're not really going to see that just yet. Okay, so what we're going to do to help us figure out where we're going up or where we're going down, okay, where is this function increasing or decreasing, we're first going to figure out the critical points. Where is there a high point or a low point? So if this is our original function, we need to analyze or figure out where is the derivative of this function equal to 0. Can we figure out the derivative of the function real easily, quickly? We got 3x squared minus 6. And if we set that equal to 0, because we want the slope to be 0 for a high point or a low point, let's go ahead and figure out those x values. Let's see, add the 6, divide the 3, square root both sides, don't forget the plus or minus. All right, so these two values here, positive square root of 2, negative square root of 2, these are classified as critical points. Those are possible locations of a max or a min. We're not sure which one is which, okay, but we'll eventually talk about how we can figure that out. But we found the possible locations. That's where you have a horizontal tangent, okay? So these are the square root of 2, it's an easy square root, nothing too nasty, but we are eventually going to have to figure out the coordinates, okay, x's and y values. So if you have a calculator handy, we're going to use it in a little bit just to plug in some numbers. But if you don't, my calculator people, I might be relying on you, okay, if you have one ready. So if these are the particular locations where we have either a high point or a low point, what we're going to do is kind of create a chart, okay, an organized piece of information to help us determine, are we increasing or decreasing before or after these values. So if you think about, notice how the original function is cubic, right? What's the domain of a cubic function? How far left would the graph go? How far right would it go? Cubic is that S shape? Curly? Isn't it all real numbers? Yeah, negative infinity, positive infinity? Okay, so what we're going to do is we're going to take the domain of the original function, which is typically all real numbers, at least for now, and we're going to break it up using those critical points. So we're going to start with negative infinity. Our first critical point in order would be a negative square root of 2. We would then go from negative square root of 2 to the positive square root of 2, and then square root of 2 to infinity. So we're taking the domain, all real numbers, and we're breaking it up with those critical points. All right, so now that we have these intervals, we're going to figure out what the derivative or slope is doing on those intervals. So in your head, okay, the square root of 2 is like 1.414, I think. Pick any number you want between negative infinity and negative 1.414, preferably something easy. Negative 2, okay. So what we're going to do is take that value, negative 2, and we're going to plug it into the derivative to figure out, is the derivative positive, is the derivative negative. If you were to plug in negative 2 into the derivative, would you get a positive value or a negative value? I don't care what the number is. It would be positive, right? Okay. So let's think about this. If the derivative is positive, what does that tell us about the original function? How is it behaving graphically? If the derivative, aka slope, is positive, it's increasing. All right, pick any number you want between negative 1.414 and positive 1.414. 0, 1, negative 1, anything you want, okay? If you were to take your number and plug it into the derivative, would you get a positive value or negative value? Negative. So, if the slope or derivative is negative on this interval, or what do we know about the original graph, the original function? It'd be decreasing, right? Okay. Last interval, pick anything you want between 1.414 and infinity. Something easy. 2. Okay. Plug 2 into the derivative, positive or negative. Be positive. So if the derivative or slope is positive, the original function is increasing. No calculator necessary, okay, to get a picture of it. Based off of this information, we could probably draw a rough picture or graph of it. Okay, we'll get there eventually. Let's go a little bit further. Can we determine, we labeled that this positive square root of 2 and negative square root of 2 were critical points. Okay, they are potential maxes or mins. Now that we've filled out this informational chart, can we say for certain if one of them is a max or one of them is a min based off of the behavior that we described? If the original function goes from increasing to decreasing, what's that creating? A max, okay? So that negative square root of 2 that we found as a critical point happens to be a maximum. What about the positive square root of 2? If the original graph goes from decreasing to increasing, we have a minimum. All right, so now that we have this informational chart, we're going to, based off the directions, it says determine the intervals where f of x is increasing, decreasing, and find the coordinates of any extrema. Okay, high points or low points, justify your answers. So let's start with one bullet point here. F of x is, maybe we'll tackle increasing first. F of x is increasing on which intervals? Look at your informational chart. We said negative infinity to negative square root of 2, but also square root of 2 to infinity. Okay, we also need to justify because. How did you know f of x was increasing? What can we use as a reason? What do you think, Justin?
F prime of x was greater than 0.
The derivative was greater than 0, aka positive. So we'll say because f prime is positive, f prime is greater than 0. Any phrasing like that means the same thing. Perfectly fine. Okay, we knew we could write increasing here because the derivative was identified as positive. That's your reason. That's your justification. Okay, let's do something similar here, but for decreasing. F of x is decreasing on the interval of negative square root of 2 to positive square root of 2 because we found the derivative or slope is negative. We doing okay? We remember these connections? All right. We also have to label some maxes and mins, okay? So we labeled, based off the chart, f of x has a maximum at the x value of negative square root of 2 because. How did we know we were able to label that spot as a max? Based off your chart. That's kind of a go-to spot. What do you think, Ariana?
Because it goes from a high point to a low point, or increases, decreasing.
Okay, so you could say one of two things here based off the chart. You could say because f of x changes from increasing to decreasing, or you could say the derivative changes from positive to negative. They mean the same thing, okay? So we were able to label the max either based off of the original function information or the derivative. Either one you want to say. Maybe I'll say derivative changes positive to negative. Okay. We also needed to find the coordinates, okay, the ordered pair. So if this is the x value of the maximum or high point, how could we figure out the y value? How could we figure out the actual height of that high point? If you know an x, how can you figure out a y? Yeah? Substitute it in. We're going to plug it in, right? Where are we going to plug it in to? We basically have two equations here. We have the original or we have the derivative. Which one represents a y value? Yeah, the original, right? Because derivative means slope. Original means y value or height, okay? So this is when your calculator might be needed. If you were to plug in negative square root of 2 into the original function, what would we get out? I need you to take the time to do that. For those of you that have a calculator, plug in negative square root of 2 into the original. Can we round it to 3 decimal places? Someone help me out? 6 point, yeah?
657.
657. There we go. 6.657. So we'll label this as our maximum value. That's our maximum height. Maybe not the highest, right? Because if you think about a cubic graph, it's going to go up forever, okay? So this is a high point on the graph somewhere, not necessarily the highest, okay? Let's do a similar statement, but for a minimum, because we found one of those. F of x has a min at the x value of the positive square root of 2 because, again, you could say one of two things based off the chart. You could say the original function f of x changes from decreasing to increasing. You could say the derivative changes from negative to positive. Okay, they essentially mean the same statement. Okay, so if that's a location of a minimum, let's plug that into the original to figure out the height of that minimum. It might not be the lowest point, but it's a low point on the graph. People with calculators, going to need you again. Yeah. Sounds good. So we'll label that as a minimum value. No calculator, unless for computation wise, but no graphing calculator needed. Okay, we did all of that analysis without using a picture. Okay, it was all based off of the derivative, aka slope. We doing okay? We're going to try another one. Okay, practice, practice, practice. Let's go ahead and check out number 2. All right, we first have to find the critical points. Where are those possible or potential high points and low points, maxes and mins? And those happen where we have a derivative of 0. So real quick, power rule, we're getting good at these. We can figure out our derivative. Let's go ahead and set it equal to 0. How might you want to solve for x in this one? Because now we have multiple x's, not necessarily the single x like the last example. Ready, Ryan? You mean factor?
Yeah.
Okay, we're going to pull out a 15x squared. That's a GCF, greatest common factor. And we're going to be left with x squared minus 1. Anything else you guys want to do? Yeah?
You can change the x squared minus 1 into x squared, or x plus 1 and x minus 1.
Yep, difference of squares, so we can factor a little bit more. All right, so we have 3 x's showing up in those factors, which means we're going to have 3 x values, or critical points. Let's see, the x squared would give us a value of 0. We would have negative 1 from the second factor and positive 1 from the third. Okay, those are the critical points. Those are possible locations of a max or a min. We're not sure which one is what just yet because we have to do that chart, but these are potential locations. Okay? So let's think about this. X to the 5th, a quintic, we'll say, graph. This is still a polynomial, and polynomials are essentially roller coaster graphs with a bunch of dips and curves. So no matter if you're talking about quintic, quartic, cubic, quadratic, all of those are all real numbers. You'll be able to trace your graph from the left to the right. So we're going to take the negative infinity to positive infinity domain and break it up in order with these critical points that we found. So negative infinity, negative 1, then negative 1 to 0, 0 to 1, 1 to infinity. All right, we're going to figure out what the derivative is doing on, or what the derivative value is on these intervals, and based off of the derivative value, that should tell us what the original function or graph or how that's behaving. Okay, so pick any number you want between negative infinity and negative 1. Negative 2. Okay, so here's the thing. We're going to plug that into the derivative. We're going to figure out what the slope is. Now you can use, we essentially have two derivatives going on here. I mean, they're the same thing, they're just in simplified form. You have the derivative at the top, so you could plug in negative 2 in there to see what you get out. Or you could plug in negative 2 into the factors. Okay, so it really doesn't matter, but strategically, I think the factors are going to be a little bit quicker, because if you were to plug in negative 2 and then square it, is that a positive or a negative value? Positive. Positive number times 15? Still positive. Okay, I'm not worried about the number. I'm just worried about the sign. So don't worry about the actual calculation. So if I plug in negative 2 and for this x, I get something positive. If I plug in negative 2 for this x plus 1, is that positive or negative? Negative. Okay, so this was positive, this was negative, and if you plug in negative 2 here, this will still be negative, right? So what's a positive times a negative times another negative? Yeah, positive. Okay, I don't care about the number value. Don't worry about the calculation. You're just worried about the sign. So if the derivative is positive on that interval, how does the original function behave? It's increasing. Good. All right, pick a number between negative 1 and 0. Negative 1/2, maybe? Negative 1/2 and square it times 15. Still positive, right? Okay. Negative 1/2 plus 1. Positive. Negative 1/2 minus 1. Negative. Positive times negative. We got negative, so the original function is decreasing. Maybe we'll choose positive 1/2 for the next interval. Plug it in. We'll have positive, positive, negative, all multiplied together would be another negative. So we're decreasing. And any number you want between 1 and infinity. Maybe 2. Positive, 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 all multiplied together would be positive. So original function is increasing. Are we okay with that chart setup? How it operates? Okay. So now that we know what the original function is kind of doing or behaving like, can we identify any maxes or mins? We said we had 3 potential ones. What do you think? Can we classify negative 1 as something? Can we classify 0 as something? Can we classify 1 as something? What do you think?
First one's a maximum, and then the last one's a minimum.
Okay. The middle one's a little tricky though, right? Because notice how there's no change. Okay? So if you were to think about this, I think we did an example maybe like this yesterday. Okay? Thanks Colton, your original graph is decreasing initially, but then it has a slope of 0, okay, at the x value of 0, and it continues to decrease after that. Did we kind of see that idea yesterday? You decrease, then you have a slope of 0, and you continue to decrease. Okay, so this is what's determined as a level location. It's not a max or a min. Okay, notice how 0 was a critical point though. It was a potential max or min because it has a level slope, bless you, but in the end it's not classified as one. Okay, that's why we use the word potential. It might not be a max or min. So let's go ahead and now use this chart and create some of our justifications. So they want to know where f of x is increasing. We also need to determine where f of x is decreasing, and we'll get to those maxes or mins. So based off the chart, we said f of x is increasing on the intervals negative infinity, negative 1, and 1 to infinity, because why were we able to write those words increasing in the chart? How did you know? Go CB? The derivative is positive. Perfect. Okay. Decreasing on negative 1 to 0 and 0 to 1 because the derivative or slope is negative. Looks good. All right, let's go ahead and tackle those maxes or mins. So f of x has a max at the x value of negative 1 because, based off the chart, you could use two reasons. The original function changes increasing to decreasing, or you could say the derivative changes positive to negative. Either one of those is fine. Okay, and if this is a max, let's go ahead and plug in negative 1 into the original to get the y value or height of that maximum. Hi, what's up?
Mr. Coulter?
Click,
They have to go up in your room somewhere today.
Today? Okay, thank you. All right, I think if we plug in negative 1 into the original function, we'll get negative 2. So we'll label that as a maximum value. Again, it's probably not the highest point, but it is a high point on the graph. Let's go ahead and label the minimum. F of x has a min at the x value of 1 because you could say the original function changes from decreasing to increasing. You could say the derivative changes from negative to positive, both mean the same thing. And let's go ahead and plug in 1 into the original function. Did I get them switched? Sorry. This is positive 2, right? Okay. And if you plug in 1, that's where you get negative 2. Okay, I was looking at the wrong one. So there's a minimum value. We doing okay? We ready to amp it up a bit? Possibly? Alright. Let's try a trig one. Alright, so for this one, trig functions, they are all real numbers because if you think about sine or cosine, they're the waves, so they do go all the way to the left, all the way to the right. But in this case, they're giving us a particular interval to work with from 0 to 2 pi. So we'll see how that comes into play when we talk about developing the chart. Let's first find the critical points though, okay, where the derivative is 0. So if you don't like those thetas, you can think about them as x's. The derivative of theta would just be 1. And trig derivative shortcuts, what's the derivative of sine? Cosine, right? So we would have a 2 cosine left in there. All right, set it equal to 0. Let's see, subtract the 1, divide the 2, and unit circle time. All right, so if you have to reference this, because this one can be a little tricky, I think your unit circle is on page 10, towards the beginning, okay? So on the unit circle, you have to find where, okay, what radian value, or location rather, does cosine have a value of -1/2? Reference your unit circle. What radian location, or locations, there might be more than one, does cosine have a value of -1/2? Can we find them good, Vinny? 2 pi over 3 and 4 pi over 3. Perfect. Alright, so we're going to take the domain, in this case the 0 to 2 pi, because that's the only section we're really working with, and we're going to break up that domain with these critical points, okay, these potential maxes or mins. So we'll go from 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, and then 4 pi over 3 to 2 pi. Alright, so if you still have your unit circle out, might not be a bad idea because we're going to have to plug in some values here. Pick some radian value between 0 and 2 pi over 3. Pi over 2, okay? So if you were to plug in pi over 2 into your derivative, we got to figure out, do we get a positive value or negative value? We got positive. So the original function is increasing. We have a positive slope. Pick some radian value between 2 pi over 3 and 4 pi over 3. Pi, plug it into your derivative. We got negative. So original function is decreasing. And then pick something between 4 pi over 3 and 2 pi. Maybe 3 pi over 2.
At this time, we are in 5:10 lunch. Again, that's 5:10 lunch. Thank you.
Should you guys be in lunch right now? Or your next class? Yeah?
Yeah.
Oh, this is so crazy. Alright. Schedule's craziness, guys. We'll pick that up tomorrow or next week.
First one.